Hi, and welcome to another Hopper internals video. Hopper is a modern curly brace and semicolon language similar to Java or C#, but designed to run on small devices like microcontrollers or 8-bit CPUs like the 6502. If you're not familiar with it, this is not a getting started video. This is more a sort of under the hood video, so I suggest looking at the other playlists on my channel first. Anyway, this video is about the virtual machine that runs Hopper. Let me just, I've got a little program here, a little sample program. I'll build that. As part of my build, I've got run disassembler to generate the disassembly from the code that was generated. So this is a typical Hopper binary. I've set tiny Hopper here, which really should be minimal Hopper. If you use that, then the toolchain, the compiler, the optimizer, and the code generator will use a subset of Hopper virtual machine instructions so that you can run this on a simpler version of the runtime that doesn't include a more rich set of the Hopper virtual machine instructions. But it's good for the purposes of illustration because it looks sort of simple, like like the kind of project you'd build in university for an education project. Those kind of instructions, very simple. So let me walk through it first, through the binary of what's been generated here. So the first 6 bytes in the binary are the header. They include a version number. There is actually a different version number for, there's a different version of the binary that I currently make, but it's usually 0. I'm still on the very first. And then it points to an offset to constant data, which is like if you have constant strings in your program, they'll be in that section. But since there aren't any, that's exactly the same as the entry point right now, which is the start of your program. So the entry point is the location of the start of the main method. For other methods, there's a method table. So method 1 here is my method, and it's over here. So the code for my method is down here, and that's its location in the file. In terms of the limitations of the size of a program in Hopper, it's relocatable. So what we're seeing that the disassembler has produced here is they're all relative jumps except for the start of the except for the start locations. They're all relative jumps. So this jump here is +6, so it says 6 here, and it's got 24 here, but the disassembler generated that hex 24 to there, but that's +6. So the limitation is that a method can only be, these are 16 bits wide, so the method can only be sort of 32K long because you want to be able to jump from right at the beginning to right at the end, so half of 64K, because you need to be able to jump backwards as well, negative and positive. So it's a signed offset. So you could actually have fairly large programs theoretically in Hopper if you made a different version of the binary that had a non-16-bit method table up front. You could have a much bigger than 64K limit to the size of a Hopper program. So I intend to do that at some future date if it ever becomes necessary. Up to this point, I've managed to stay within 64K for all the big tools I've created, which includes this editor, the debugger, the compiler, preprocessor, optimizer. The biggest programs by far are the debugger, because it includes stuff that knows about the runtime and also stuff that knows about the source. Like it's a combination of the editor and the compiler. And the compiler itself is pretty large as well. It's also close to 64K. So if I run over that limit, I'll come up with an optional version that deals with this. Well, now 64K seems okay. But in the future, it could be much bigger than 64, where the limit would be you can only have 32K methods in a very large file. All right, let's get on with it. So that points me to where the start of my program is. And the start of my program happens to be before line 13. So in my code here, let's have a look. It's line 21. So the first line in my program here is actually, line 7. It's line 7 down there. So where's line 7? Oh, it's in there somewhere. It's the start of the program. So what this is doing here is, oh, it's line 13. Here's 13. I'm in column 7. Yeah. So line 13 is here. So whatever is after this is line 13. So what's before line 13 in my main method? Well, there's this here, which pushes a 0 onto the stack. And what that's doing is it's initializing my global variable, because everything is on the stack, including global variables. So before I enter my main, the global variable must exist on the stack, or at least a slot for it. And in Hopper, there's no such thing as an uninitialized variable. Everything is 0 initialized by default. So A is going to be 0 by default. Then we hit enter. And what enter does is it sets up a stack frame, and very common for stack-based languages. So there is no accumulator or other utility registers in the Hopper virtual machine. There are only 3 registers: the program counter, the stack pointer, and the base pointer. So the stack pointer is what you think it is. Actually, there's a 4th register as well, which is the call stack pointer, because it's got 2 stacks, a call stack and a value stack. And it makes just for much, if it's not hardware, if you're doing it in software, you can create a much simpler stack machine if you have 2 stacks. So what does enter do? Enter sets up the stack frame for the method. Very common in these kinds of designs. So what does it do? It pushes the base pointer onto the call stack and then moves the stack pointer into the base pointer. And at the end, in the return, it undoes that. So it will pop the previous base pointer on exiting. And what the base pointer does is sets up a stack frame so that you can use relative offsets from the base pointer. Here you see BP plus 0. So BP plus 0 is the first local variable in the method, as opposed to inside this method where it's dealing with a global, which has got an absolute offset of 0. So the first global, this A thing, it was at location 0 on the stack. So you're either going to use relative addressing or absolute addressing: push global and push local, or pop local and pop global, to push and pop. And the reason you have a base pointer and you set up the stack frame when you enter a method and undo it when you exit the method is so that you can call recursively. And the code in here, even in recursive calls, can find your local variables and also your arguments. The arguments have a negative offset from the base pointer. But that's I can talk about that more in a different video. So we've seen push immediate pushes a 0 onto the stack. Enter, we understand what that does. So I here is for immediate. Hopper is 16-bit stack frames, so even if it was a byte, it's still going to push 16 bits. If it was a reference type, the 16 bits is the reference, sort of like a pointer, but you can't actually ever get to them, and there's no such thing as a null pointer. Then it comes into my program. So we want to initialize a value with 2. So the unoptimized, naive way of doing this is to push a 0 onto the stack to make a slot on the stack for your variable. Then we push a 2 onto the stack, and then we pop whatever's on the top of the stack, which is now this 2, into that slot we made, which is at base pointer plus 0. That's how we initialize the value to 2. Now we have an if statement, which is on line 15. Yeah. If value equals 0. So again, it's just popped that value into there. Now it's going to push it again. So it's pushing the value from BP plus 0, which is my value. It pushes a 0. And then most of the instructions, arithmetic instructions, etc., work on the stack, just like this equals does. So what equals does is it pops 2 values from the stack, compares them, and then if they're equal, it pushes a 1 onto the stack for Boolean true. If they're not equal, it pushes a 0 onto the stack for Boolean false. There's also something else to know, and that's in addition to the 16-bit stack slots, there's a parallel stack with the types. Currently implemented as 1 byte, so it's really 24-bit stack slots. And that'll have a Boolean when it pushes this one, and whereas it had a uint for these. So it's got runtime type checking, which helps it make it easier to implement things like variant types. So you can have like a list or a dictionary that's full of variant types. So at runtime, you want to make sure that So at compile time, you can't tell if the thing's being passed to your code is the correct type or not. So it does have some runtime type checking as well. It does as much as possible with static compile time type checking. Anyway, so that's what equals does. So it'll pop two values, compare them. If they're equal, push a 1 onto the stack. If they're not equal, push a 0 onto the stack. And then the jump instructions all look at the stack for 0 and 1. So there's three kinds of jump instructions. There's just a jump instruction without checking anything, just an absolute jump. I mean, an unconditional jump. And then there's conditional jumps, which are basically either 0 or not 0. So because I want this to be true to go into the if block, it must be a 1 to go into the if block. So if it's 0, it'll jump past my if block. So if it's 0, it jumps forward by 6, offset of 6 to here. And that's the end of my program. And it returns. If it's 1, in other words, not 0, it'll jump into my block here, where I've got a function call. And I did this function call. I'm going to show the optimizer later, and I don't want it to be optimized away. So it's calling method number 1. And then it goes and looks up where the address is from this method table up here. And that's at address 17, and off it goes. And this gets optimized on the microcontrollers and on the 8-bit devices when the first call and lookup gets made, this gets swapped with another call instruction, which calls an address instead of calling an offset, which would be something else that would have to be dealt with if we ever went more than 64 bits. Anyway, so it enters my method. Here's my method. And again, I deliberately made this method have a global side effect because I don't want it to be optimized away. I don't want it to do nothing. But I also want the code here to be quite small so that I can show how the optimizations work. Anyway, enter, same thing. So that's stack pointer goes into push the base pointer, stack pointer, enter base pointer. Then it pushes this global variable from offset 0. And then it pushes a 1 onto the stack because a++ is increment a. So it pushes the global variable's value, pushes a 1, calls add. That pops two values, adds them together. And then it pops the result from the stack back into the global variable, and then ret 0. And ret with a 0 means it's returning, so it's restoring the stack frame again. In other words, popping the BP. But it's also got no locals or arguments to pop from the stack, and that's what the 0 is. Whereas if there were local variables, here it's popping 4 bytes from the stack, so two 16-bit slots. So one of those 16-bit slots was our local variable that we created, and the other one is the global variable, because at the end of the program, it's going to pop the global variables too. And we could insert some checking here. If we go create a check build, and then we have a look at what happened to the code, it added this test at the end, test BP, and it added another test over here. And these tests to check that that the stack is balanced in the way we expect it is. It does a lot of other checking as well, like range checking and range checking on accessing things like arrays and lists and strings. But we'll turn it off again for now to keep it simple. We won't create a check build, so we'll get rid of that again. All right. And so all these methods made sense, right? So now the first thing we're going to do is we're going to turn off this tiny hopper, which should be called minimal hopper, and we're going to build again. And now we're going to use a wider range of instructions. And the program gets a bit smaller because there are so many things that are super common that it's worth making instructions for them. For example, pushing an immediate 0 value might as well be a 1-byte instruction. So in the previous version, when I had this up here, it was 3 bytes to push a 0. So it had this instruction, and then the operand was a 16-bit integer, and that's true of everything. So push local offset 0 is 3 bytes long. The globals as well, 3 bytes long. So all the pushes and pops are pretty wide, so it's a lot of code. So we're up to, say, address 32 hex in terms of the size of the program, plus the operands, but that's close enough. So if we get rid of that, how much smaller do we get? So we got 32, 33, 34 hex. And if we do that, we're down to 1E hex. So significantly smaller in terms of the actual footprint of the code by using methods for common things like this push 0 is very, very, very common. And then the push local 0 is also very common because and local 1 is also a shortcut method that's one, special opcode that's 1 byte long. And so the pushes and pops of the zeros are common because often a method will only have 1 or 2 arguments or 1 or 2 local variables. So you can get to them with 1 byte instructions. All right, so the same thing's happening right now. It's still pushing a 0, pushing a 2, popping it into local variable 0. The if statement still looks very similar, but it's just pushing the 0 differently, pushing the local differently. It's still calling equal. It's equal still the same, and then when it passes there, the call is still the same. This ret b is, so the b thing here and the b suffix here mean that the operand's a byte. So if it's a small number like 2, it doesn't need to push 16 bits, it can push 8 bits, and that's the same for returning 4 bytes. So ret b is, it's very unusual to have to pop more than that, and even more so like ret 0, which is very, very common, is also a single instruction. It looks, so now when I'm running this way, if I create a checked build, it doesn't run the peephole optimizer either. So you get push the global, push 1, add pop global for A++. If you don't create a checked build, so we're still not running the optimizer. This is just the peephole optimizer that's built into the compiler rather than the whole program optimizer. It replaces that with inc global. So increment the global variable at absolute offset 0. So 1 instruction instead of 4. Anything else that got smaller? That's all for now. Okay, and then we go and go for the big guns, which is the whole program optimizer here. And so what are we at? We're at 1E hex size. So let's build it again. And this is with the whole program optimizer and the peephole optimizer. And the program gets a lot smaller. So this is the optimized version of this program. We're down to 1.2 hex in size. So it's done a couple of things. There's something called enter B because it's very common to create stack slots when you enter a method. And this is why we didn't optimize the initialization. So it can create all of those, like if you had 6 global variables here, it would create them all in one line with, it would be like create me 6 stack slots and instead of creating me 1 stack slot. So this is actually in 2 byte increments. This 1 here is creating this the slot for this value variable. And this is still the same, initializing by pushing 2 and popping it into local. And the if statement suddenly got very interesting. It's instead of 4 instructions, it's now 2 instructions. In global is still the same, but an interesting thing happened to this method. Let's have a look at it. So it's jumping to the method, which is, I believe it is gone. It inlined the method. Method's gone because there's no longer a table here. So it saw that this inc global 00 was actually smaller than the method call, or the same size as the method call. So the amount of actual execution happening in the method was only 2 bytes. So it just inlined it into the main program. And then ret b 4 is still the same. All right. Let's focus on this area right now. So if I turn off optimizer and put that again. So the if 0 part was 4 instructions here. So what did the optimizer do? Well, if value equals 0 means that it's going to push that, push value, push 0, compare them to each other. If they're the same, push a 1 onto the stack. If the value on the stack is 0, jump past and don't execute my block, right? Now, if I optimize, it's going to switch this from a jump 0 to a jump not 0. And so what it's doing is it's seeing that this condition here is the same as saying jump if not 0. That's like saying jump if not 0 based on what's on the stack. So it just pushes the value and says jump if not 0 past. So it does a lot of these sorts of optimizations. And then there's something else some variation I wanted to show about this. So if we go greater than 0, it can't optimize it away, right? Because it's not sure what value is. So if it's negative or not, because it's an int, so it's a signed type. However, this is a reason to use signed or unsigned types. Like if you're doing something like a loop that's using an unsigned type for I equals 1 to 10, then you should use an unsigned type, and here's why. So here's the greater than again, right? Still greater than. We compile that, and it's optimized the comparison again, right? Why is that? It's because when you've got a signed type, it can never be negative. So greater than or equal to 0 simply means not equal to 0. So jump if 0 passed. Otherwise, it's not equal to 0 going to the block. So a good example of why you should use signed or unsigned types to reflect what your code's doing. So let's do, what's this? Not equal to. See how that optimizes. Same one-liner. What about greater than or equal to 0? That shouldn't optimize because it could be either. Greater than or equal to 0 is actually quite interesting. Okay, let's do it this way first. So if it's signed, it has to actually execute that, right? Because it could be negative. So it needs to check. It needs to, and you can see the greater than or equal to actually has an I in it, meaning that's an int greater than or equal to rather than an unsigned int greater than or equal to. It's a different opcode. So if I make it into an unsigned int, what is greater than or equal to for an unsigned int, right? It's always true. So it can never be negative, so that's always true. So what happens? It's gone. So it just removed it as dead code. So there is no jump anymore. And that's the smallest version of the program we've seen so far. Anyway, I think this is a good place to end in terms of how the opcodes work, how the virtual machine works, and how the optimizer works. Let me just have a look at the options quickly just to walk through them so that you know what they are. So the one at the bottom, save on build, that means that I don't have to be prompted every time I make a change. So if I make a change and press build, are you sure you want to, do you want to save before you build? Okay, right. So that's that one. Run disassembler, you only need it if you're looking at the disassembly like we are, but it's also kind of handy if you have a red screen of death. We can simulate that. Value by 0, right? And so let's compile that. And we're gonna push the variable push 0, divide, and pop, which is not going to end well for this thing, but we'll go out to the console and we'll go test2 and run our program. And we end up with a division by 0, which is error number 4. And we end up with a, we should do it inside our method. Let's do that, make it more interesting. So let's do it inside our method. A equals A divided by 0. Yeah. And then test2. That's better, because now we have a call stack. That's interesting, right? So this I call the red screen of death. And there's a utility called RSOD, red screen of death, and you type in the name of the program, and it used the debug info to find the point of failure in my program. So if you ever had a crash that didn't get caught by the system, now we know where it happened. So it happened on line 9. I think it happened after line 9, but close enough. Yeah. I think that's the last line number that it was aware of before the crash happened. But anyway, that's what the red screen of death's about. Okay, what else can we show? Run disassembler I've mentioned. Generate ihex. If you're uploading to a microcontroller, then you want to generate ihex. So if I do that, and then when I compile, now I've got launch debugger, which I didn't have previously. So if I F5 to launch the debugger, it uploads it to my microcontroller. I've actually got a microcontroller connected right now, Raspberry Pi Pico, and it's uploaded the hex file to the Raspberry Pi Pico. So now I can step into it and my full debugging experience is happening. So this code is executing on my Raspberry Pi Pico. It did something funny there because it was inlined. So sometimes it's not obvious what's going on, especially with things like inlining. So if you're debugging on your microcontroller, you might do it without optimization. So now it should step into my method like that. And then we can see the call stack here. Where'd I come from? Came from there. There I am. So you can double click on the call stack to navigate. Anyway, this code's all executing on the Raspberry Pi Pico. And I can do things like I can dump the memory. So memory dumped. And then if I go in here, there should be a memory. So this is my current memory dump from the device. And it's the stack trace on the left here. There's not much of it. And then what's on the heap, which is things like the breakpoints used by the runtime actually get stored on the heap. These are two tables that get used for optimizing array access for Boolean arrays, bit flags. And then this here is the free list on the heap, which currently is just one big object. That's how much is free on the heap. And this is how much memory is used. So you can dump memory from your microcontroller while it's running. Right, let's go back to the options. Extended code segment. It's a short-term fix for programs like the compiler and the debugger, which are getting close to 64K, where what it does is it puts the string constants into, so I can actually, so if I go const string, the string equals a whole bunch of values, let me compile that. Oh, it's not used, so it throws it away. So how do we make it use it? I think it'll still, even though it's not doing anything, that'll use it. So that's another interesting thing to know. It doesn't matter what code you include or in your project. If it doesn't end up compiled into the binary, it gets thrown away as dead code. So we've now got a constant block, as I mentioned earlier. So the offset of the constant data is there, and the offset of main is beyond it, right? If you use extended code segment here, I'm also not running the optimizer right now. If you use extended code segment, it'll change the binary version number to show that it's different. So now the binary version number is 1 there. And what it's done is it's rewritten when you load this. So where's the main entry point is no longer at 23, it's at 0. And my offset of my method is at 1A, which looks like it's over here, but it's also over here. So what has it done? What it's done is it started the 64K code segment over here. So it gave me back what was used by the constants no longer. So that's the extended code segment. So it puts the constants into their own 64K segment. And why would that be interesting? So if you go and look at the compiler, there's the method table for the compiler. It's pretty big. And up top here, it's got a 1 at the end, so it's the extended version. And we scroll and we scroll and scroll. There's lots of methods in the compiler. And here are the constants. There are 8K of constants in here. Actually, it's not 8K. I think that's hex. Is it? Don't know. Not sure. Oh, yeah. We can see on the left here. It's 8K. And then the code starts at 0 here. So it gives me a whole extra 8K by not including all these constants in the main code segment. I could compress these at some point, but that's a trade-off between speed and space. Like, loading up time would be slowed down, or access time would be slowed down if it was compressed. So it was an easy way of making my 64K just for code and another 64K just for data. Came about when Swedish dude Niels is working on a fourth interpreter written in Hopper, and he had a massive chunk of data which was his predefined fourth words, and it was an enormous set of constants, and it chewed horribly into the code segment. So that's when I first implemented it. Anyway, that's about as much as I'm going to say about the Hopper virtual machine and environment for now. I think this makes a good internals video. I look forward to feedback and comments on this, and if there's anything else you'd like to know or other areas of the Hopper environment you'd like me to talk about on the internals playlist, let me know. Thanks. Cheers.